Good afternoon, everybody. Our next speaker is Christopher Neugebauer, giving a talk on the complexity of simplicity. Chris used to run PyCon AU and has passed those reins over as he has moved to the US. He is the director of the Python Software Foundation, a contributor to pants, which we're all wearing, of course.
Wait, what?
And yes, probably one of the people at the conference who needs the least amount of introduction because you all know him so well. Please help me give a warm welcome to Chris.
Oh no, an audience. I was fearing this. Hi everyone. This is another one of my talks about how Pythonistas think about software engineering. I've been giving talks in this vague direction for like 5 years now. And because I've been doing this for 5 years, things are now starting to get scarily abstract, for which I apologize. There is less code in this talk than my talk tomorrow will have. Unfortunately, for those of you who've seen other talks where I make old versions of Python do weird things, I'm not doing any of that today. I apologize. But you're here anyway. Thank you so much for coming along. Shall we begin? So here is a value of Python's. Simple is better than complex. And what better way to demonstrate Python's simplicity than with the first Python code that most people write? Let's talk about print. Print, it is the first function I see introduced in most introductory Python textbooks. Understanding print is very, very simple. You call it, unlike on this slide, you normally give it an argument, and then some text gets displayed to the screen. Wonderful. But what does print do? Who here knows what print does? Print does a lot of error checking. Here's the actual implementation of print. It's taken from the very source of CPython. The function is called built-in print impl, which is complexity that you didn't need to know about. That's the function that actually gets called. It's quite long. There is a lot of error checking. Here is the line somewhere in it that actually takes an argument, writes it to what will usually be standard out. And the bit that's really important is this bit here, the bit that says pyfile_writeObject, which itself has a whole world of implementation details to worry about. And you're looking at this, and what's actually important about this is none of what you're reading. The important thing is that this is C. And this is a Python conference. And so for you and me as Python people, understanding the C API, is this going to add an undesirable amount of complexity to this talk? But I'd like to take a moment to point out here that this is already complexity that's inherent in doing something very, very simple in Python. Rather than just executing some code that's written in Python, we are executing C code. Python needs to allow you to run C functions, and to keep that overall simplicity, it needs to present these C functions to the rest of the language runtime in exactly the same way that presents your Python functions. And the C API that's needed to facilitate all that is complex. You saw all that error handling. But this is a Python talk, so let's talk about Python. Print to a Python developer has a complex interface with complex behaviors that really depend on how you specify these keyword arguments at the end. And that's complexity that I don't want to touch. So we're going to narrow the scope even more. Let's talk about printing just one thing, just a single argument. So what we're going to do is we're going to define a variable, and then we're going to print the value of that variable. And if we set the value of our variable to a string like hello world, this is very simple. How would print work? Well, we can iterate over each of the characters in the string. We can write each character to a file, standard out, in sequence. It doesn't actually work like this under the hood. You saw that earlier. There's some complexity that involves block I/O, which becomes more efficient if you transfer in larger blocks across the API boundary. But eventually there's something that's just going to go through every single character and put them onto some sort of buffer somewhere. So there's already a whole bunch of conceptual complexity here, but it's not too bad. As a Python person, what if we want to print an integer? Well, this code is going to throw an index error because you can't iterate over an int object. This code won't work. So what you need to do is you need to stringify the parameter that we pass into print. And under the hood, well, stringification will look something like this. You dereference the type of the object, and you call the done-to-string method that's on that type, pass in the parameter that was passed. And with that, you can print anything reasonably. But in reality, this stringify code is probably provided to the C library, but if we're not going to use that and to deal with this complexity, we're going to write our own stringifier, which needs a bunch of knowledge of ASCII and stuff. And that's before you even get to that implementation of this putC function that I didn't even talk about, which is underpinned by a whole bunch of sophisticated software and hardware concepts that will eventually give you the ability to see the text that you ask to be displayed on your screen. Nobody sets out to write complex code. There's two things that you should have learned from that discussion of print here. The first is that we should all want to interact with the simplest interface possible. And the second is that even the simplest thing you can teach someone about programming hides a lot of complexity under the hood. I don't think that anyone would disagree that the best, most maintainable code is the simplest code that you can write under the constraints that we have to operate in. As software, it exists because there is complexity inherent in the world, and if we can model that complexity, then we help people navigate that complexity. And by helping people navigate complexity, if we do it right, things become simpler for them. Now, looking at print is instructive. It only appears simple, whatever that is, because we wrote building blocks, and with each tool, from the LCD elements in our projector here, right up to the Python interpreter itself, more complexity gets modeled and simplified for us. Which is leading me to some indisputable facts here. The first is that complexity exists, that it will be experienced by somebody on a project of some description. It could be an end user, it could be you as the programmer. And on a systems design level, complexity is either modeled or ignored. And more importantly, that simplicity usually belies some level of complexity on some level within a system. Put another way, anyone who is experiencing simplicity is doing so because complexity has been dealt with in some sort of way. So with that in mind, I used to think about how to build the simplest possible solution to a problem, which raises the question of what we might think is simple. And I don't think this is a good question anymore. I don't think it scales well. Instead, if we accept that simplicity will usually belie some sort of complexity within a system, then the questions we should be asking is, who should be experiencing simplicity within a system? Which parts of our system should be simple? And where should simplicity be experienced? And the main thing that I want to convey is that the answers to these questions are in flux. Python is an evolving ecosystem, and as new problems arise and new tools make different problem domains easier to navigate, our focus changes, and our focus will continue to change. So, the first idea that I want to explore is the idea of internalized versus externalized complexity, which is one where Python has really changed its tune over the last 10, 13, 15 years thereabouts. There used to be this idea that Python would come with everything that you needed to solve most problems you might ever encounter out of the box. And this idea was prevalent back around the time the Zen of Python was actually written. It's actually less relevant for these days for a number of reasons, but that's not particularly important right now. Who's seen this thing? Firstly, ignore that it's a joke at the expense of Perl. This line was written as a joke. There's still enough people in the Python community who take this seriously. And so Python had this idea that if it made the big decisions for us about how you'd solve your problems, then everyone would have the same version of Python, and you could read another person's Python's code, and that would be great, and everybody could understand everyone's code. So we're going to talk about a thing called urllib2. So that two there, that's entirely down to Python not addressing the complexity of namespacing in the standard library, which they fixed in Python 3. They called it urllib.request, and that introduced complexity in reading documentation, which I'm not going to get into, but that's a thing as well. URLlib2 was built around the idea that your code could be simpler if you could just drop URL handling code into Python code that dealt with other interfaces. And so it did all this in what would be a relatively familiar way to you. Your request objects, they kind of quack like files. There's an object-oriented interface for installing handlers for more complex use cases, and you could install these handlers for authentication and redirect handling, either with or without affecting global state. And so in doing so, it let you do a reasonable job of modeling the complexity of working with perfectly specified HTTP. But how does that look in practice? So URLlib2 has a thing called authentication helpers. What you do is you create a password manager to associate some credentials with specific URLs. That's this HTTP password, blah, 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 blah thing. And you can create an authentication handler that supplies these login credentials. And then you create an opener that knows how to open URLs with these auth credentials. And you use that opener to open the URL. And then you treat the response like a file, and you hand it into json.load, which I presume you've imported somewhere in this code before. This code becomes visibly simpler if you choose for URLlib2 to not manage the complexity of authentication for you. As long as you know how to write this header, you can make a request with that header. And with this, you're forced to make a trade-off. You either get simple code and you model the complexity yourself, or you have the complexity handled for you, but you spend a lot of time rigging up this reusable authentication handling infrastructure. And so the alternative is that we use a different library like requests. The behavior around authentication is a lot more declarative in requests. You say you want bearer auth, you make a request using those declarations, and as a bonus, you don't need to think about file handling because it imports JSON for you. And this is obviously much simpler code to interact with an authenticated HTTP API. You can make use of the library's work to model the complexity of authentication, and you get short code. You don't need to make these trade-offs within your code. But what's particularly interesting about this is that requests chose to re-implement something that existed in the standard library, and then it chose not to be in the standard library itself. This was a very odd choice at the time. But in retrospect, this is how things tend to get done in Python these days. By being out of the standard library, Request was able to adapt as the broader web communities changed, their attitudes changed, particularly around things like security. And it chose to model some complexity of interacting with HTTP services for end users. And as a result, the code that you need to write to interact with requests is much, much simpler than interacting with URLlib2. So the question that arises from this is, what do you get for that gain in simplicity? Is this absolute? And the answer is no, this gain is not absolute. Now you need to model dependencies. You need to have a requirements.txt. You need to write instructions on which requirements.txt file to load with pip. You need to manage execution environments. You need to keep things up to date. And so there's now added complexity in maintaining a project. So which is the right choice here? Well, if you're making the choice to use requests or URLlib2 in 2011, the choice might not have been immediately clear. I think people were still thinking about whether using virtualenv was the right thing to do or not. And this was still fairly early in the trend of HTTP APIs where everything is an API now. It wasn't the case back then. So maybe if your application needed to hit a number of services that looked like GitHub, and regularly you might do that, but if you are fetching packages off a Debian mirror or something like that that doesn't require authentication, URLlib2 might have been simpler for you. And so you'd have a bit more first-party code wherever you needed to hit a weird API, but your overall code base would be smaller with URLlib2, and you wouldn't need to track external dependencies. And the alternative would be to have less code, but more complexity in terms of the environment that you need to manage. I think in retrospect, this idea of less first-party code and letting your dependencies do more of the work is an approach that is won. And this is not because absolutely everything was in place 10 years ago. It's because we saw this as kind of a good way forward, and we built tools to help us manage complexity that arose from deciding to manage external dependencies and configuration. We have things like GitHub and Git more generally to manage our configuration management. We have reasonable tooling for managing execution environments, and we have a quite good package index. And so now we're in a place where our definition of simplicity has actually changed. For an identical problem, a modern Python code base is going to be smaller than one that we wrote 10 to 15 years ago to solve the same problem. But the trade-off is that we have an increase in complexity of configuration management. So we have more dependencies, but we have more rigid environmental requirements. But those dependencies, they model complexity themselves. We have configuration tools, they model complexity. And so for the modern Python developer, it seems that we get simplicity as a virtue of other people managing complexity for us. And just as a thought, like if simple is better than complex, well, what does it say about how good the code that we're using to manage our environmental complexity is? So the second idea I want to talk about is one that's less conclusively answered in Python, which is the idea of how we go about managing complexity in a code base, and whether the tools that we have actually present us with simplicity. And specifically, I'm going to talk about quality assurance, which is the set of tools that we use to make sure that our programs do what we say or do what they're meant to do. But first, let's talk about duck typing. So duck typing is an idea that two objects are interchangeable if you can use them in the same place and not get interface-related errors. If you're a type theorist, you would call it structural polymorphism. I'm not, so I won't. Python's use of duck typing is a very, very simple type system, both to implement and to understand. Firstly, there's no syntax in the language that describes the types that exist on an interface. You just have functions and variables. This is simpler than Java or C++, which require you to enumerate the types that an interface expects. And then on the other hand, there's no automatic coercion, so the language doesn't do complex behavior to make data behave in different contexts. This is simpler to JavaScript or Perl or PHP. This forces some complexity in terms of managing types onto you as a developer. When faced with some library code, you may ask yourself, well, how do you make sure that your library code is correct? And that normally comes down to two questions, which is, what does your code do, and where should your code be used? So let's talk about this first one. Well, how do we solve this what does your code do problem in terms of quality assurance perspective? It's to do things, test, do your numeric inputs work, do your strings work, do your valid non-numeric inputs work? Things that you write with tests. So automated tests help us manage complexity of verifying behavior by allowing us to automatically run code that will check the code that we're verifying under the test works. And to go back to this talking about computer science terminology stuff I was doing earlier, what we're doing is describing a set of things called invariants. An invariant is basically a specification of some behavior that a system should hold, given a set of circumstances. If an invariant stops holding, then either the behavior is wrong or the specification is wrong. And the more invariants you describe, the narrower the set of behaviors your system can display, which means that the more invariants you have specified, the more your complexity is managed. And a unit test is a way to specify an invariant. The circumstances are this data that you provide to the function under test, and the invariant is a set of assertions that are specified about the result. And this is really familiar to us. It gives us a simple code-based structure to reason with, which is that functionality lives in the implementation files you have, and invariants are specified in test files. But what if we think about our simple framework for quality assurance? Well, we've only really looked at one of these two questions, the question of what our code actually does. If we're thinking about these and giving them fancy names, we can classify these two questions into functional style invariants, which are the things that specify how the thing works, and structural ones, which is how a piece of software fits into a system around it. And the tool that we have for describing functional invariants, I don't think, are very good at describing structural invariants. We can describe where things will work, but we can't really exhaustively describe where things won't work. And in Python, for the longest time, we kind of solved this problem with documentation. On the other hand, we have types now, and types are great at specifying structural invariants, and recent versions of Python can describe types for most reasonable Python code. As well as providing structural invariants, you also don't need to write as many tests. So if you can't specify the wrong type, you don't need to enumerate all the cases where you might have a type error. You can't specify the wrong type, so you don't need to test those things. But I'm not here to evangelize types to you. I think they're great, but they still aren't universally popular. And there are really, really good reasons for that. Firstly, types are a tool for managing complexity that really only occurs in large code bases. And it's not always clear when you've crossed the line of structural complexity that arises where you can no longer fit things entirely within your head. I don't even think it's always clear that a code base will ever achieve the level of structural complexity where you need to have typing in place. And generally, it can be hard to judge when types are necessary. And once you do, you kind of have to learn to use an entirely new system, which itself can be a complex thing. And so you end up with a trade-off. You can either have a simpler toolbox for managing quality assurance, or you can have a simpler way to specify the structure of your code base. And so you can either have more tests and more documentation, or you can make your interfaces harder to read and harder to understand. And so there isn't actually a correct answer here yet, I don't think. I think both approaches provide some sort of simplicity depending on what sort of problem you're trying to solve, but they both leave complexity elsewhere in a project depending on how big it gets. So I'd like to finish up with a discussion of evolution of Python itself, because a common complaint I hear is that Python is becoming more complex with every single version, and I think it's worth taking some time to examine whether that is the case. So Python was, for a long time, a completely static language for a lot of us. Python 2.7 was around for a very long time, and that's kind of the time when a lot of the growth of Python actually happened. And it was only really around Python 3.5 that the language started to become stable for people who needed to do Python, who needed to use Python 3 for things other than data science. And the language has kind of been adding on language features very regularly with every single major release of Python. But if you're used to Python not changing on you for 7 whole years, then maybe you'd be asking yourself, well, what happened to this idea of simple being better than complex? To which I would respond with print. Because Python has always been a language that kind of tries to model complexity so that users can write simpler code. And one thing that happens as more people from more diverse use cases decide to use Python to solve their problems is that we discover more cases where Python is just not simple to use yet. So Python just models more complexity for us. Most of us really, when we first learned Python, only really picked up a subset of Python as a language. And likewise, as new features emerge, we'll only ever need a subset of these new features. As somebody who writes APIs for things, I don't need a matrix multiplication operator. But then again, a data analyst is probably never going to need to write an async await coroutine in their Jupyter notebook. I was at Kiwi PyCon last year, and I gave a talk there, and I tried to make a point that Python's success was its willingness to support use cases from a diverse set of disciplines. And another talk called The When of Python argued that you can very easily use a subset of Python's features and never need to think about the more complex features until you actually need to use them. And they even proposed a model for it. It's called The When of Python. I don't entirely agree with it, but I think it's a good start, and you should look it up and either adopt it or criticize it. Basically, go to last year's Kiwi PyCon. There are videos. And that's the secret. Like this complexity is reasonably self-contained, and it's optional until you need it. And this stands in contrast to needlessly complex languages like Java, or even necessarily complex languages like Rust. We as programmers want to continue to model more things, and then the question we have to ask ourselves is, well, do we want to have a simple language, or do we want to write simpler code with the language that we end up using? Right, so now we're at the end of the examples section of this talk, and we're going to enter into the realm of commentary again. So when we started, we had this proposition that simple is better than complex, and we went through a bunch of examples that show that when you are writing Python, somebody is going to have to model complexity for us. And in the world of Python, we're really lucky that the language we use chooses to model a lot of complexity for us, and it provides tools that can model new and unexpected forms of complexity. But I haven't really spoken about code that we write ourselves, which brings me to this thing that I said at the top of the talk, which is that complexity exists. It would be better if complexity didn't exist, but it does, and as developers, we can choose to contain that complexity, or we can choose to do not contain that complexity. So what I hope I've conveyed today is that we should be thinking about who should be experiencing simplicity and who should experience complexity. You know, we work in narrow domains as developers, and so even as if we're working in a team on the same project, different people focus on different things. With each of us having a pretty good understanding of the stuff that we work on ourselves, and so it's probably best if we model our own domain's complexity so it's not complicated for other people. And this is why you can have a giant pile of C code that does a whole bunch of stuff and then present a coherent interface that is safe to give to new programmers as literally the first thing we teach them. Like, that's the point. Our code has end users, whether they're consumers or whether they're other software developers on your own team. Your code is almost always going to be part of some bigger system, and it will exist because it's modeling some sort of complexity better than a human could. Your code has dependencies. Each of these dependencies, from the Python interpreter to the packages your dependencies depend upon, model some sort of complexity so that you don't have to. Otherwise, it just wouldn't be useful for you and it wouldn't need to exist. And maybe your own code is somebody else's dependency chain. We've seen earlier in this talk that the things that may be simplest, they can change as we get newer tooling that solves problems more repeatedly, or if people's opinions about what is good changes. We've seen that what's simplest may depend on a trade-off between more upfront work and deferring decisions until later. For me, a guiding principle is that simplicity can be a gift that you give to others. If simple is really better than complex, then leaving your end users with a simpler experience and managing your own complexity is probably better, because that means that you're the only person dealing with this complexity that you have to deal with. Also, I lied. This is a slide that suggests that you should definitely use types, if only at your interface. Types at your interface give your users less complexity to need to worry about because you've told them what things will never work with your code. Choose to model complexity for your end users and annotate your interfaces with types, if nothing else. More generally, simplify things appropriately, because I think this is what you should take away from this talk. The idea that simple interfaces are a thing that we should strive for and complex ones are not. But if you simplify things in the wrong place, you tend to remove so much complexity for us to be useless and inactionable. And you get talks like this one. Three minutes for questions? Okay, apparently we have time for questions, so Jacinta is going to hand a microphone somewhere, and we'll see if anybody has a question. You can ask the obvious one as well. Yes, Tom.
What's the obvious question?
Do you have your laptop out?
Yeah.
You just type import this into a Python interpreter.
Okay.
Yeah, and just read what it says there to yourself. I'll just give you a moment. Have you found it?
I know it.
Okay, well, do you want to ask what the question is then?
Well, I guess now the question is, how do you know if it's simple if you're Dutch?
That wasn't the question, I'm sorry. Does anybody else know what the question I've prepared for is?
What is the question you prepared for?
No, you don't get that, sorry. Thanks, everyone.
Is complex better than complicated?
I'm not answering that. All right, thanks, everyone, for coming along.